Hello everyone, I'm Benjamin Reidys, a PhD student at UIUC. I am presenting our work, RSSD, which leverages hardware-isolated network storage Codesign to create a fundamental solution to encryption ransomware attacks by enabling zero data loss recovery and trusted post-attack analysis. This work is done in collaboration with my advisor, Dr. Jian Huang, and Dr. Peng from Penn State. Ransomware attacks are a major threat in today's world. 2021 saw the Colonial Pipeline attack, attacks on American football teams, attacks on schools and hospitals, and ransoms as high as $30 million. Altogether, this paints a pretty bleak picture, which requires our attention. So what is encryption ransomware? Typically, attackers start by deploying malware to gain access to the victim's system. They then encrypt the victim's files, destroy the original copies, and demand ransom to decrypt the data. To defend against ransomware, software-based approaches have been developed, such as malware detection. However, files encrypted before detection cannot be recovered. One alternative is to use software-based data backups. However, ransomware can obtain OS kernel privileges and terminate or destroy these data backups. Due to the shortcomings of software-based solutions, researchers have developed hardware-based solutions against ransomware. In particular, they exploit the out-of-place updates intrinsic to SSD's flash storage to retain victim data. To facilitate the discussion of hardware-based solutions, I will discuss some basic information about flash storage. Here we have a flash block, which consists of multiple flash pages. A page can either be free, meaning it can be written to, valid, meaning it can serve reads with valid data, or invalid, meaning garbage collection, or GC, must erase the block before that page can be written to again. When we update X to X prime must be written to a free page, and X becomes invalidated. Note that X is retained until garbage collection frees this block, meaning it can be used for some time for recovery. Currently, ransomware does not differentiate between the underlying block I/O devices, whether or not it's an HDD or an SSD. However, we believe that this will change. SSDs are becoming increasingly popular, so they will become increasingly targeted by ransomware and bypass existing hardware-based solutions. We also observe that adapting to SSDs requires few changes. To demonstrate ransomware's adaptation to SSDs, we identify 3 new attacks circumventing SSD-based protections that we call Ransomware 2.0. First is the GC attack. The GC attack leverages the insight that once garbage collection removes the retained data, it is no longer available for recovery. To that end, the GC attack dumps large amounts of data to fill the free blocks of the SSD and trigger GC. GC will then remove the victim's data. Second is the timing attack, which leverages the same insight, but hides its operations by waiting for the user's own storage operations to trigger GC on their own. The result is the same. Finally, we have the trim attack. For performance reasons, modern SSDs include a trim operation where systems can directly notify the SSD which blocks can be erased. Ransomware attackers can use this in order to directly target retained data. To see this attack in detail, let's go over first the GC attack. It begins by encrypting the victim's data. It then writes a large quantity of garbage data to fill the free blocks of the SSD. When it runs out, GC is triggered, and the victim data is removed. For the timing attack, we begin by encrypting the victim's data. We then let regular storage operations from the user happen, filling the free blocks of the SSD. Once we run out of free blocks, the victim's data is removed, and the attack succeeds. Finally, the trim attack. Again, we encrypt the victim's data. We then issue the trim command to the retained blocks. The next time GC is run, those will be removed. Ransomware 2.0 shows us that ransomware can and will evolve to circumvent defenses in new and unpredictable ways. We need a fundamental solution to protect against future evolutions in ransomware. In particular, Ransomware 2.0 showed us that we need to strengthen the data retention of hardware-based solutions. Therefore, a fundamental solution will need to implement zero data loss recovery. If we can recover all of the victim's data without paying the ransom, then ransomware attacks will stop as they are no longer profitable. Second, we must be able to learn evolving ransomware patterns. To that end, a fundamental solution will need to implement trusted post-attack analysis so that we can understand ransomware trends and adapt to them quickly. To implement zero data loss recovery and trusted post-attack analysis, we design a ransomware-aware SSD we call RSSD. Since local storage capacity is limited, we leverage remote servers to retain stored data. RSSD achieves this by integrating a hardware-isolated network component and uses NVMe over Ethernet to transparently offload the retained data to remote servers. Second, RSSD achieves trusted post-attack analysis via hardware-assisted logging of all storage operations within the SSD firmware in time order. We integrate both of these components into a single SSD by modifying the architecture and firmware. Incorporating these features into a single SSD means we can strengthen our threat model. In particular, we do not trust the upper-level system and choose to only trust the SSD firmware. This achieves two benefits. First, the SSD firmware has a smaller trusted computing base, making it generally more secure. Second, it makes us hardware isolated from malicious processes underneath the block I/O interface. This is particularly relevant for ransomware, since attackers are often in the system long before they deploy the ransomware, giving them plenty of time to deploy other exploits. However, developing RSSD is not easy. We have to overcome the following challenges. First is the limited local storage capacity. We overcome this by using delta compression on the retained data and network storage codesign to transparently offload stale data to a remote server in a hardware isolated manner. Maintaining stale data will inevitably incur overheads. Therefore, our second challenge is how to guarantee good performance under these conditions. We do this by keeping all valid data locally and only transferring data over the network during idle cycles. Finally, we must enable trusted post-attack analysis entirely within the SSD. To do so, our SSD first tracks all storage operations in the SSD firmware and tracks them in time order both within the SSD and in the remote server. First, let us discuss the limited local storage capacity. No matter how effectively we use the local capacity, we will eventually run out of space as we retain data. Therefore, we leverage remote servers to expand the local storage capacity. In the traditional manner, we would need to export this data over the block I/O interface to the host network and then to the remote server. However, we do not trust the upper-level software, as they could tamper with this procedure. Therefore, we integrate a hardware-isolated network component into the SSD. To begin, in a secure environment, the user can configure the connected remote servers using the control register. This is disabled during runtime for security. During runtime, the DMA engine copies retained data from the onboard DRAM into the transmission queue, which are transferred to the remote server without being exposed to the host. This is feasible since it only adds 5% area overhead and consumes minimal power, and the existing SSD architecture with the embedded processor and the onboard DRAM facilitates this data pipeline. Second, we consider the performance optimizations to avoid interference from retained data. First, since page updates are typically quite small, and we naturally retain the old versions of data, we can use these small changes, or deltas, to enable delta compression. This gives us two benefits. First, we can reduce the storage overhead, and second, this reduces the amount of data that we need to transfer over the network. Second, since users rarely access the retained data, there is no need to keep it locally, and for performance, we export it aggressively to remote servers. The transfer of stale data helps free space for the SSD to use for local operations. Finally, there are often small gaps between user storage operations that we can leverage to transfer stale data without interfering with storage operations. To predict the next idle time of the SSD, we use a simple exponential weighted moving average. If we mispredict, we suspend the transfer until the I/O is complete to avoid interference. Finally, we must enable trusted post-attack analysis. Post-attack analysis seeks to track the history of operations that lead up to an attack and use it to learn ransomware patterns. This is critical for victims and law enforcement to understand evolving ransomware trends. To understand the state of the art, we conducted a study of recent major ransomware attacks and found that only 24% report conducting post-attack analysis. And this analysis took on average nearly 6 weeks. Even worse, this analysis happens at the software level, which means this logging cannot be trusted. Therefore, a trusted post-attack analysis solution is highly desirable. And we enable this in RSSD with hardware-assisted logging by tracking all storage operations within the SSD firmware in time order. Let's first discuss how we track writes. Writes are tracked via the invalid pages that are implicitly created by each write. And we track these with a set of Bloom filters. Each Bloom filter represents one epoch, where there is one active Bloom filter for a given epoch. The invalid page is inserted into the currently active Bloom filter. When GC seeks to transfer a page, it checks all the Bloom filters before transferring. If it finds a page in any of the Bloom filters, it keeps the page locally for now. As the Bloom filter fills up, the active one becomes inactive, and the oldest inactive Bloom filter will be replaced with a new one. By resetting the oldest epoch, we free the oldest pages to be transferred by GC to remote servers. For read operations, we do not track read operations in the same way since they do not produce invalid pages. Instead, we track them in a separate buffer in the SSD DRAM that we flush to the flash as it fills up. In the buffer, we track the LPA of the read page and the timestamp at which each read occurs. The trim command also uses a buffer to track the history of operations, but we need to do one more thing to secure it. Remember that modern SSDs can issue the trim command directly erase targeted blocks. Attackers can use this to erase retained data. To secure it, we give the system the illusion that the trim command is successfully executed by remapping the block to a free flash block. In either scenario, the system sees a free flash block and cannot tell the difference. However, we are now able to retain the data that was supposed to be trimmed, and by treating them as pages invalidated by writes. To summarize, locally, we keep invalid pages, read operations, and trim data. In the background, we use the network and idle cycles to transfer this data in time order to the remote cloud. To see how RSSD defends against Ransomware 2.0, we review the attacks we first proposed. To defend against the GC and timing attacks, we can leverage the retained data either locally or in the remote server to recover the data that has been removed by GC. For the trim attack, by changing the functionality of the trim command, we retain the victim data while giving the system the appearance that it succeeds. Finally, since we enable zero data loss recovery and trusted post-attack analysis, we successfully defend against future attacks as well. We implement RSSD on a real-world FPGA board and evaluate it using traces from real ransomware samples collected from VirusTotal. We evaluate SSD from traces from MSR, FIU, as well as real workloads that we trace ourselves. First, we test the impact that RSSD has on data retention time. Here we compare the local SSD, which is an SSD that retains pages locally, naively, local SSD plus compression, which compresses the retained pages, and RSSD, which is our solution. To test the retention time, we fill the SSD to 50% and start running various real-world traces to mimic storage operations. Local SSD can retain data for 1 to 11 days before filling up and rejecting writes. Through compression, local SSD plus compression is 6.4 times more effective. RSSD is even more effective than this and can retain data for over 200 days by transferring data to the remote cloud without rejecting writes until the SSD is truly full entirely with valid data. Next, we evaluate the impact on storage performance, in particular the average latency of I/O operations. We add regular SSD here, which is an unmodified SSD. We fill the SSD to 80% and run the corresponding traces. Our evaluation shows that naively storing data, comparing regular SSD and local SSD, results in almost 2 times overhead, as fewer available blocks result in intensive GC operations. If we compare RSSD, we add only 1% additional overhead compared to previous solutions, resulting from transferring stale data over the network. In summary, we present 3 new attacks to represent evolutions in ransomware and identify zero data loss recovery and trusted post-attack analysis as critical to preventing these evolutions. We build RSSD to implement these with network storage Codesign and hardware-assisted logging. Thank you very much for listening, and here's my email if you want to contact me to follow up with any questions.